Okay, let's get started. So today's topic is retrieval-augmented language models. This is going to be the last topic that is fair game for your midterm next week. So we won't be covering any new information before the exam. So after today, you should be able to proceed with all your preparation. Again, the exam is open book and open internet, so when you are studying, make sure to focus on the concepts and not the low-level details, which you can easily look up in the papers that are referenced in the questions. All right, so any questions about the exam week before we get started? All right. So today we're going to be talking about essentially how do you augment your language models with knowledge that comes from an external source and is not learned intrinsically within the model's parameters. So for example, when we look at something like BERT, BERT already encodes a lot of knowledge from its pre-training objective, right? So if we take this example, Bob went to the mask to get a buzz cut. And if you pass this through the BERT model, you'll see that the resulting predictions make sense, right? Like barbershop, barber, salon, stylist, these are all places where you might expect to get your hair cut. And so BERT is actually showing that it's encoded some world knowledge about like where you get haircuts and so on. So possibly augmenting BERT with knowledge of something like a barbershop is where you get your haircut is not particularly useful because during its pre-training phase, it already was able to encode information about this concept. So in one of the readings for today, which was the Realm paper of Gu et al., they make this distinction between knowledge that is learned and stored implicitly within the model's parameters. So like we don't exactly know how BERT was able to get to this predicted distribution, but some parameters that are part of BERT were able to, during the computations, increase the probability of barbershop here. So we might not know what exact neuron in BERT is responsible for the barbershop concept. Probably there isn't such a thing, and maybe it's a group of neurons that are across many layers or many heads or something like that. It's hard for us to know exactly where this knowledge is stored, but we do know just from looking at these predictions that it's stored somewhere, right? So this is some kind of knowledge that is implicitly stored within the model's parameters. If we're talking about, all the knowledge from our pre-training corpus must be stored within the parameters of the model, then it kind of makes sense why, as we scale up these language models to bigger and bigger sizes, we see improved performance across basically every task, right? And in last class, we saw that if you have a fixed size model, the capacity or the ability of the model to perform well on multiple languages goes down as you increase the number of languages, which seems to indicate that increasing the model size is the easiest way to increase its capacity to handle multiple languages. And this general concept likely also holds true for just arbitrary knowledge that the model can memorize and put somewhere in its parameters. So, of course, just brute force scaling up these models to bigger and bigger parameter sizes is not particularly interesting or accessible to like 99.9% of researchers or even industry practitioners. So today we're going to talk about an alternative where the model is not forced to store all of this knowledge within its parameters, but it can actually query a database or some sort of external knowledge store for useful information that can help it make these predictions. So this kind of work has been going on way before neural language models were popular. There's a lot of work on knowledge graph completion or induction or construction. One of our faculty members here, Andrew McCallum, has done a lot of work in this area. And so here you have your knowledge represented as a graph. So nodes in the graph are generally like entities. So here we have shape of you is a song, Ed Sheeran is a node in the graph, the genre pop, and the whatever this is, another song, and so on. And you can see that the edges of the graph correspond to different relations, right? So shape of you is sung by Ed Sheeran, who's also the singer of Castle on the Hill, right? So you can imagine if you had the ability to construct some sort of huge knowledge graph that had every possible entity and relations to other entities in this graph, or maybe events or other sorts of terms, this would be very useful when applying a neural language model, right? Maybe the language model could easily look up and then traverse this graph to figure out what entity should I generate conditioned on what I've seen before. However, this is not very easy at all, right? First of all, we don't have such a huge knowledge graph because most of these large-scale knowledge graphs are either very, very expensive to create, and you can't just update them easily with new information. Some require a lot of manual effort because you have to curate, what types of edges are you going to consider, what types of nodes, and so on. And there are automatic ways to get these kinds of graphs from text, but they're noisy, not very reliable, and you might lose a lot of information. So you could, in theory, if you had some giant knowledge graph that was, highly precise and also had huge coverage over the entities in the world, think about applying a neural language model, like integrating that with this graph to get better predictions. And people have tried, but this is not really a very scalable way to move forward if we're thinking about the general language modeling task. So one huge advantage of having a knowledge graph is that the graph structure itself makes it easy to navigate and find different relations and entities that are related to a certain thing in the graph, right? You can imagine all sorts of traversal algorithms or even learned agents that can traverse the graph depending on some input. However, they have a lot of downside. So they're expensive, as I mentioned. It's the automatic knowledge graph induction is a challenging open problem. It has not been solved. And also, what happens if you have some sort of very complex relationship between two entities that it doesn't really make sense to boil down to like a single edge on a graph, right? That could also be a concern. So as an alternative, we have another source of knowledge, which is unstructured text. So unstructured text, you can imagine like Wikipedia articles, right? They have no structure. I mean, okay, Wikipedia has like headers and formatting and stuff like that. But compared to a graph, they are basically unstructured, right? There are sentences. You have to have a model that can actually understand the content of those sentences and extract the relevant pieces of meaning that are needed to improve the language model's prediction of the next word. So there are pros here, right? It's very cheap to collect unstructured text. I could just, download the Common Crawl or whatever. And we have pretty good methods now of encoding text, unstructured text, right? We have seen things like BERT, for example, are very useful in computing semantically meaningful representations of input text. So of course we don't really have a graph structure, but we still know that these representations are very useful. They contain information about the important entities and relations that are expressed in that text. So there are some downsides. We don't really know how to apply these methods to longer units of text yet, and this will be a topic of a lecture after the midterm. Models that can scale to long documents instead of just the small chunks of text that we've seen so far. And also, of course, extracting information is nowhere near as clear when you have like a dense vector than when you have a graph with these clearly defined nodes and edges. So today's lecture, we will be focusing just on if your knowledge store consists of unstructured text. For example, Wikipedia, how can you use this to improve the performance of a neural model? If you're interested in this kind of work, there are definitely many papers that people have developed a lot of methods to try and interface language models with knowledge graphs, but we won't talk about those today. Okay, so I wanted to start with the Realm paper, since this was probably the first paper to integrate this kind of external retrieval from an unstructured knowledge base into a neural language model like BERT. So here, if we start with this example for the masked language modeling task, the mask at the top of the pyramid, and we're going to call this X. So remember that when BERT gets an input like this, its goal is, after it passes this whole text into the model, it will get a vector for each one of these tokens. And for all of the vectors that are associated with the mask tokens, we're going to put a softmax layer on top to predict the identity of the mask token. Right? So in normal BERT, I would just pass this through BERT and put a classifier over this mask token and see what it says. But in Realm, which is the retrieval-augmented version of BERT, we have an intermediate step first. So we take this sentence with the masked out token, and we use it to retrieve over a huge data store of documents. In this case, they were like chunks, so small paragraphs from Wikipedia, basically. So we have what they call a textual knowledge corpus. You can imagine that this is just all paragraphs from Wikipedia for the sake of intuition. So each of those paragraphs is going to be embedded using something like BERT. So you get a single vector that represents each paragraph. You could do this by simply taking the CLS token after passing each of these paragraphs through BERT. So now you have one vector that can be constructed from this mask token or from the CLS token associated with this input, and you have a bunch of vectors that correspond to the paragraphs in your data store. So we have first a module called the Neural Knowledge Retriever, which, given these two inputs, will retrieve documents that are most similar or most useful for for predicting this mask token, essentially. So these could be paragraphs that are talking about pyramids or things at the top of pyramids. As you can see in this example here, they retrieved a paragraph that said the pyramidion on top allows for less material higher up the pyramid. So here, this document contains hopefully the correct answer to this mask token, right? This says the pyramidion is at the top of the pyramid. So if we have a retriever module that is kind of integrated with the training process of this BERT model, now the BERT model, this one that's predicting the mask token, doesn't actually have to memorize this fact that the pyramidion is the thing at the top of a pyramid. Instead, it can rely on the retriever to provide this information. So you can see that this general concept of retrieving is a way to get around just blindly scaling up your model. Because now, if you have a good way of encoding external knowledge, you can instead have your model first retrieve relevant documents and then condition its prediction on the retrieved documents. Does that make sense?
How do you train the retriever? Like, do you have to do backprop?
Yeah, so we'll get to that in a second. Is there another question?
Wouldn't it be more time consuming?
Wouldn't it be more time consuming to do what? Yeah, so this is quite expensive, right? If you imagine you have every single paragraph from Wikipedia and you're doing a retrieval on top of that, that could be very expensive. But luckily there are very efficient ways of retrieving based on dense vectors that are used in all of these kinds of approaches. It's still slow, but it's manageable. So one of the methods we'll talk about later on in the lecture, they say that it's 2 orders of magnitude slower than generating without retrieval. So in practice, that is probably way too expensive to deploy in a system. But I mean, these are all still at the early stages. So things will improve hopefully, and the performance is better when you do this. Okay, so to your point, we'll talk about how to actually train this thing a little later, but I just wanted to go through the full pipeline first. So assume you have this retriever module and it can retrieve these relevant paragraphs. Now, instead of just predicting the identity of the mask token conditioned on the surrounding context, we're just going to simply concatenate the retrieved text to this input before we actually do the mask token prediction. So now I have the mask at the top of the pyramid, the separator token, and then the text from the paragraph that I retrieved, which clearly says that the pyramidion on top allows for blah, blah, blah. So remember that in BERT, my self-attention is not masked. And so when I'm predicting the identity of this mask token, I'm actually, the representation has attended to all of these tokens in the future, including this pyramidion token. So that's why you might expect the prediction of pyramidion here to be much better than without this retrieval. Okay. And so finally, we put a classifier over the mask token to predict the distribution of what goes in there, and that's just the same as in normal BERT. We use softmax layer to do that. So essentially the only new thing in this pipeline is we retrieve a paragraph, we concatenate that paragraph with the query, which is our initial training example with the mask token, and only then do we predict the mask tokens. So let's start by going over how you train this retriever, which is the most important part of this whole setup. So if you look at this, so y here is the what is going into the mask token. So the p of y given x, x here is the original input with the masked out pyramidion word. So p of y given x is a distribution over all of the words that go into that mask token, right? So in order to predict p of y given x, the realm system decomposes this into 2 different steps. So first we retrieve document z, and then we predict y given both z and x. So you can see down here that the probability of y given x is, and let's ignore the summation for now, given that we've retrieved article z or paragraph z from our initial masked out context, then we model this probability p of y given z and x. So now the crucial point is that we don't know which paragraphs are going to maximize this conditional probability beforehand, right? We don't have any training data that says, oh, well, when I get this context, I always want to retrieve this particular passage, right? There's no way for me to get this kind of data. So the model actually has to learn which documents are more relevant than which other documents for maximizing this probability. So one way you could do this is simply do this retrieval, retrieve every document, and compute this probability, and then sum over all of the documents. And so maybe this would be a good way to go, except this is obviously incredibly expensive to do, right? So if you were able to do this, then the model might learn to put high probability on z's that maximize the probability of pyramidion in that context. That's what you would want. However, we can't do this simply because this big Z here, the set of all documents, is extremely large. And you can imagine for a single mask token, if I put in like 5 million paragraphs from Wikipedia, concatenate each one to the context, and then do this prediction, it's going to take forever. There's no way I can do this. So what they end up doing in this paper is something more simple. They have a scoring function that will take a dense representation of X and a dense representation of every single paragraph in their data store. They will perform an inner product, so just a dot product between the query representation and all of the passage representations. And so going to your point, this can be accomplished using fast nearest neighbor or fast inner product algorithms, which scale sublinearly with the size of the data store. So they're slow, but they're not as slow as you might expect. And so now we get a ranked list of all of the passages by this dot product to the query. And in the Realm paper, they take the top K of those, where K is usually 5 or 8 or something like that, and they marginalize over the top K instead of all possible documents. So this is, of course, a big approximation. So now in this function here, this candidate set consists of only the top K highest scored retrievals instead of all possible documents. But in practice, it seems to work fairly well, and they're able to learn a model that actually retrieves useful passages. So there are some tricks associated with getting this to work. The models that you're using to get the dense representations of X and the documents Z need to kind of be pre-trained so that they start from the inner products are meaningful when you start training. If you randomly initialize the models that are responsible for computing those representations, this doesn't work at all. So there are some tricks that are needed to get this to work. So, okay, let's break this probability down a little further now that we roughly know how this works. This P of Y given Z and X is basically just BERT, except the input now has concatenated passage from Wikipedia in addition to the example itself. So nothing fancy here. We know how to do this. We just put a softmax layer over the mask representation, and that's the probability of Y given Z and X. So the more interesting part is this P of Z given X, the probability of a document being relevant to this particular mask prediction given the input query. So how do we actually model that? And like I explained briefly before, we are going to model this using a very simple inner product. So we basically just need a way to get a vector for X and a vector for Z, and then we take the dot product, and that's our score, which we will just normalize by all of the scores in the data set. So we'll get a distribution here by just dividing by the sum of all of the inner products from all of the passages in Wikipedia to this particular input X. And so this function f of X and Z is just some dense representation of X and the dot product of that with an embedding of the document. And they use BERT, the CLS tokens, to get both the input of the embedding of the input and the embedding of the document. And crucially, these are different BERT models than the one that is responsible for doing the mask token prediction. So the retriever has different parameters than the model that's responsible for predicting pyramidion in that example. Okay. So, like I said, to get the embedding of the input, we basically will just take the CLS vector, so BERT CLS, of passing that input into a BERT model. So you can kind of ignore this join BERT thing. It's mostly there because to embed a document from Wikipedia, they take both the title of the article as well as the paragraph. They concatenate them together, and then they take the CLS representation of that input. I think they took the title because it's pretty informative as usually in Wikipedia it's an entity or something which can help with the matching process. But conceptually, we are just taking a BERT model, passing either the input or the passage from Wikipedia into BERT, and then taking the CLS token. And then this equation is just the CLS token corresponding to that input that still has a mask token. And this is the CLS token corresponding to the passage. We take the dot product, that gives us our score for one query and one passage. Are there any questions? Yeah, so I mean, this is showing it without that approximation, but yeah, in practice, when you do the nearest neighbor lookup, they're only retrieving the top k, the ones with the highest dot product, and they then do the marginalization over that. So yeah. Yeah. You calculate the scores for all of the z's. That's right. But I actually am not sure if the algorithm will return these normalized probabilities or the unnormalized scores. Yeah, I'm not sure if it makes a difference because you can always normalize over the top k as well. Yeah, that's something to look up in the paper maybe. It might depend on what algorithm you're using to retrieve the top k nearest neighbors. Okay, so let's then get to the encoder, which is a thing responsible for predicting the identity of the mask token. This we won't need to go into too much detail. Basically, once you have retrieved a passage Z, we join it X and Z into a single sequence by just concatenating using the separator token, and then we do our normal prediction of the mask token based on this new input. So this is using a BERT model that is separate from the passage and input encoder. But conceptually, you can use any method to get a vector for these two things, this embed input and embed doc. You could just average word embeddings. You could do whatever you want. In their experiments, they found that BERT works the best, which makes sense. Like it takes into account word order. It's quite powerful, encodes lots of other stuff. So it makes sense why they use that. Okay, so isn't training the retriever extremely expensive? I think we already talked about a lot of this. This marginal probability requires summing over all of the documents in the knowledge corpus or data store or whatever you want to call it. They do this by summing over the top k documents with the highest probability. So I suppose to your question, they do get the normalized probabilities for the top k documents. And as they say, this is reasonable if this distribution is peaked towards a very few, a small subset of the documents and mostly zero elsewhere. If the distribution is flat, that would indicate that, you know, like most documents do contribute something to the prediction of this token, or most documents don't really give you any information at all. In those cases, this approximation wouldn't be very legitimate, but yeah, they need to do this, otherwise it's not possible for them to train. And the fact that this works with some tricks is an indication that it's an okay approximation to make. Okay, so we won't talk too much about the algorithms that are used to make the inner product search. So finding the passages that have the highest dot product with the query vector X. There's a class of algorithms called maximum inner product search, or fast approximate maximum inner product search, where you can tolerate some errors if maybe it doesn't retrieve the exact highest scoring document, but it retrieves some high scoring ones. The trade-off for this lack of accuracy is that it scales sublinearly with the number of documents in both time and storage, which makes it, in general, pretty useful. So there are some very interesting demos of these kinds of algorithms available online that you can check out that even run on CPU and not GPU and operate very fast. So over like a data store of billions of representations. So it's not very slow. One thing that we have yet to talk about, though, is that to compute the maximum inner product, you need to actually have an embedding of all of the paragraphs in Wikipedia first. So you need to run every passage in Wikipedia through BERT, get the CLS vector, and only then can you run this algorithm. And if you're training the embedding function here, embed doc, if you want to train that such that that embedding function kind of knows like which documents to give a representation for, which will kind of maximize the probability of a mask token, right? Ideally, you want to train this function. Then it becomes extremely expensive to recompute the representations of these passages every time you update your embedding function, right? And so if you imagine in one batch, I perform the retrieval with the current embedding function. I get the top passages with the highest inner product. I concatenate them with the inputs. I pass them through my BERT model. I get the cross entropy loss on top of the mask tokens. I do backprop. That backprop goes all the way down into my document embedding and input embedding functions, which themselves are like transformer BERT-like models, right? And so now I've updated my document embedding model, but since I've changed it, I now need to re-embed all of the passages in Wikipedia, which is hugely expensive. So how do I get around this? And this is called refreshing the index, essentially. So I have new vectors. I have to rebuild an index in order to do my fast inner product search. And one of the things that happens is that our embeddings in the data store or the knowledge corpus become stale, because now I've updated the parameters of the retriever, and if I don't refresh the index, then my embeddings are now out of date with the current state of the document embedder. So what they do in Realm is kind of another hack to get around this, where they know that it's way too expensive to refresh their index every single batch. So what they do is every 100 batches or something like that, they will recompute, they will re-embed all of Wikipedia using their updated document embedding model. And between these refreshes, which happen asynchronously, the index is allowed to go a little stale, but not like super stale. So this is kind of a hyperparameter that you can tune how often do you refresh your index based on your compute that you have available and how much time you want it to take. But like this is very expensive, so you don't want to just do it after every batch. So basically, like they have these two processes, the index builder and the BERT, the mask language model predictor. And so sometimes, the index builder with the embed document function will get these updates, but the embeddings themselves won't be updated until 100 iterations later or something like that. Okay, so you can tell that in order to integrate retrieval into these language models, there's a couple hacks that need to happen to make this whole process feasible. But on the other hand, now your model essentially has access to all of Wikipedia, and it can essentially look up information that it thinks will be useful to filling in these mask tokens. Since this work, there have been many improvements over this process that have come out. Recently, there was this paper by, I think, DeepMind or Google called Retro that significantly expanded the size of the data store to a really big scale, and they showed that with a relatively small language model, augmented with a huge retrieval data store, they can solve some tasks on par with or even better than GPT-3, which is, of course, like a huge parameter language model with no external retrieval functionality. So this kind of thing seems pretty promising moving forward, although training is still expensive and inaccessible to most people. All right, any questions about Realm?
Do you know, like, roughly-ish how many parameters were in the embeddings that Retro used for all the documents?
I'm not sure. You mean the dimensionality of the?
Like, I guess you said it had a giant database, right? So you have many, many documents, and then each document has an embedding.
Yeah, so there's some function, probably some like BERT-like model or something like that, that is computing those embeddings.
Okay, but then, like, really, how big is their database? Like, is it like similar scale to GPT-3, or is it just like all the?
Oh, you mean the parameters that are associated with? Yeah, it's actually significantly larger, I think, than GPT-3. But again, those are not parameters of the model. Although you can make arguments that, you know, at test time, you have to query over this huge scale data store. In Retro, that doesn't happen every token, though. I think it happens like every few tokens or something like that to minimize the cost. But the language model itself, excluding the external data store, is much smaller. So yeah, that's a good point, though. All right. So, right, there are a couple other tricks in Realm that I didn't mention, including the, not including the ones that I've already talked about. One that I think makes a lot of sense is what they call salient span masking. So here, when you're training your BERT model and you want specifically the retrieval to help, you know that the retrieval is going to help mainly in kind of making better predictions of entities or dates or very specific facts, right? Like the pyramidion is some sort of rare entity that maybe you don't want the model to memorize in its parameters, but is something easily accessible by querying a data store. So to kind of encourage this behavior, they mask out spans of text in their masked language model that are corresponding to named entities, so like names of people or things, and dates also. And these are cases where the model especially benefits from retrieval from an external data store. Finally, they also include an empty document in the top K retrieve docs. So they basically force there to be an empty document, which essentially allows the model to still encode stuff into its, implicitly encode knowledge into its parameters. So for example, if something comes up over and over again in the pre-training data, perhaps it's much more efficient for the model to just memorize this or encode it into its parameters rather than have to retrieve it every time. Maybe it can do some more fine-grained retrieval if it already has some information about this concept encoded into its parameters. So that's why they include this null document as well. Okay, so the evaluation of Realm, they did a couple different tasks. The one we'll talk about today is open domain question answering. So you can imagine this is kind of like the squad style task where you get a question and the answer is a span from a passage in, say, Wikipedia. What we saw in squad, though, is that you're given the passage ahead of time. So you're like, you know, who starred in the Matrix, and you're given a paragraph that contains the answer. That's the squad style setup. In the open domain setup, you are not given that passage. So you just get the question. You first have to retrieve a passage, and then you have to extract a span of text that answers that question. So it's basically first retrieval and then apply a standard squad model on top of the retrieved passage. But it's hard to do the first step, right? Because you need to retrieve something that has a high probability of containing the answer in it. So they tried this on several of these open domain settings, natural questions being one such data set that is quite popular for open domain question answering. And I think these are F1 scores. You can see that compared to models that do not use an external retrieval component, so T5 we talked about is just a sequence to sequence model. It will get the question and then have to generate the answer. So there's no retrieval component. It has to rely on its parameters in order to, on the knowledge encoded just in its parameters to solve this task. You can see that it gets up to 34.5 F1. And the performance, as usual, increases as you increase the size of the base language model. However, Realm, which is just a BERT-sized model, so it's much smaller than this T5 11 billion parameter model, outperforms it on this task, and it gets a new state-of-the-art on this natural questions open retrieval setting. So you can see here that this model has 330 million parameters. BERT, by contrast, has 110 million parameters. So why do you think that this Realm model has exactly 3 times the number of parameters as BERT? Yeah, so essentially Realm is composed of 3 BERTs, right? There's one BERT, which is doing the masked language modeling task. There's one BERT, which is responsible for encoding the query, which is just the text with the mask tokens. And then there's one BERT, which is responsible for encoding the document, right? So there's 3 different BERTs. It's exactly 3 times the size of the single BERT model. You can see that this T5 model has 11 billion parameters. So this is much, much smaller, but outperforming it because of its reliance on the external data store. Okay, so finally, let's take a look at an example of Realm in action. So it got as an input a query. An equilateral triangle is easily constructed using a straight edge and compass because 3 is a blank prime. And now it's asked, so this blank is a mask token, and it's asked to predict what goes in there. So without retrieval, the probability of the correct word, y equals Fermat, given this input is quite low. And then you see here that when it gets the correct document, or when it uses its retrieval and then augments the input with the retrieved document, here it says 257 is blah, 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 Fermat prime. Thus, a regular polygon, blah, 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 is constructible with compass. The probability of Fermat, given that you append this document to this input, is 100%. So it was able to basically just copy this information and use that in getting its probability distribution. Now, when you marginalize over the top 8 retrieved documents, which is what they do, this probability goes down to about 12% or 13%. Why do you think that is? Right, so maybe this is the only relevant document that contains Fermat prime, and the other documents say some other type of prime which misleads this model, right? So it really depends on the composition of the top 8 documents and how many of them are actually relevant to the input X here. So this gives you one of the open challenges in this kind of setup, right? We need ways to improve the retrieval function such that we're retrieving more and more similar and relevant documents. If the documents are not relevant, this could actually hurt. They don't show it hurting in this example, but you can imagine a case where the top 8 documents are not relevant at all, and this would just hurt. All right, so that's all I had to say about Realm. Any final questions? Okay, so let's switch gears here and now talk about, oh yeah. Yeah, that's a great question. So the question is, let's say we're using this kind of setup to do generation, like maybe not of mask tokens, but like left to right generation of one word at a time, like we saw with T5 or something. The question is, in that kind of setup, do I do the retrieval before generating each and every token? Or do I do this retrieval maybe once and then generate a whole paragraph or something and then redo the retrieval after that? Is that your question? Oh, yeah. So in this setup, you basically will append each of the documents to the input and then compute the probability distribution and then marginalize over that. But in the other scenario, you might retrieve the top 8 documents and concatenate them all to the end of the input, and then you don't have to do this. There are many different techniques that people have looked at for doing this. The other question that I thought you initially asked, there are also many approaches. Some people do the retrieval before every token, which is hugely expensive, as you can imagine. Some do the retrieval only once and then generate like a whole document with a static retrieval set. One of the things we'll look at the end of this lecture does that. But yeah, it's kind of like a trade-off between how much time you want it to take during decoding time and how much you want the retrieval to actually help. Because if you're doing the retrieval at every token, it's going to be much more relevant to the thing you're immediately generating next than if you did the retrieval like 200 tokens ago. All right, so we'll switch to a different kind of method, which is even simpler to understand and requires no training of an external model at all. So there's, we're going to go through nearest neighbor machine translation, but this is an extension of a method called nearest neighbor language models that was proposed a couple years ago. And the intuition behind this is that, let's say you have a pre-trained language model. You want to augment it with retrieval, but you don't want to train any sort of external retriever. You don't even want to modify the parameters of your language model. Can you still benefit from doing retrieval? And the way that they do this is you take your training data set, you encode your training data set using your language model. And so remember that in a transformer style language model, you have a vector at every single token that's produced, right? Your final layer vector. So you can form a data store by just taking all of these final layer token level representations in your training data and putting them into your data store. And at test time, when you are confronted with a new sentence, you can retrieve using dot product the training vectors that had the highest similarity to the current test vector that you have. And then you can just augment your predicted distribution with the words that follow those retrieved training examples. So we'll go through what that is here in the context of machine translation, but it's basically the same in language modeling. So let's say that again, we're talking only about test time. There's nothing happening. There's no training, no backprop, anything like that in this, this method. So here we have a test input, this French sentence, which I will not pronounce, and we are translating this French to English. So far we have already produced I have. Our decoders produce those tokens, and we're trying to produce the third token in the English sentence. So that's our goal. So currently, the representation of my decoder is this vector, and this is what I'm going to try and feed to my softmax layer to predict the next token. So normally, I would just put this thing through my softmax layer, and I would get the distribution, and that would be my answer to what is the next word. But in this method, I'm first going to do a retrieval where this vector forms my query And my training data forms the keys or my data store. So during training, I have all these French sentences and I have the decoder's token level representations. So I have this input and this decoder has produced I have the vector at this point that I've cached from training time. So these, as you can see, form the keys. And so we have like I have, I had, I enjoy, I have, and you see the French sentences over here too. So the decoder's representations, of course, are using cross attention, so they are also a function of the French sentence. So you can see that some of these sentences, even though the English prefix matches up exactly to what we produce, they don't seem like they're equivalent to this sentence that I have as my input at test time. Although this one, the last one, seems pretty close to the thing that I have. Again, I'm not sure what this actually means, but judging by the string overlap, it seems pretty close. So now I have this query vector and I have all these key vectors. I can just use a dot product here, and I will get a dot product, a score, for each of these training examples. Basically, this is measuring how similar is this decoder context to each of these training contexts that I've observed. And my keys are additionally going to come with the next word. So I'm going to associate these key vectors with what was the ground truth next word that followed this representation at training time. So this particular case, I got the word been next in training. In this case, it was also been. In this case, it was summer, so I guess this means I enjoy summer. And here it was my. So our goal is to predict at test time what is the next word given this context. The idea is that maybe some of these words that we saw that followed vectors that were similar to this one, but we saw during training, maybe some of these words could actually be the word that we want to predict here. And how can we take advantage of that? So first, when we do our, so here we're still going to use our fast inner products algorithm. We're going to get these approximate distances. These are just the dot products. I mean, they've been, you know, these are just example hypothetical numbers, not actually what you would see. But we see that this vector had a distance of 4 from the query. This one had a distance of 3. And this one had a distance of 1, which means it's the most similar of these that are shown here to the query vector. This one, meanwhile, I enjoy summer, is quite different from the input. So now we're going to take the top k of these, just like we saw in Realm. And here they show maybe they took 3 of them. So, and they're going to order them by the distance. So this bottom vector and this my here, which followed it, become ranked at the top by the distance, and then the 2 bins from this vector and this vector are ranked second and third. Now we're going to normalize these by just applying the softmax to get a probability distribution of the next words. So again, we have done no training at all, right? This is basically, we have taken some training tokens. We've looked at what is the word that followed this vector in the training set, like what was the word that was supposed to be produced, and we are forming a distribution out of those next training words using the dot product as the distance measure, and we're just normalizing it into probabilities using the softmax function. And then finally, you notice that 2 of these 3 items are bin, so we can aggregate those, and our final distribution puts 40% of the probability on my and 60% on bin. So now we could say we're done, and that this is our final predicted distribution for this, this test time token. But would we want to do that? What are some issues with doing that? Yeah, so we barely use this thing at all, right? We are just taking our decoder's representation and then looking for similar vectors in the training data and then looking at what comes after those. But what happens if there aren't any similar tokens or similar vectors in the training data to this, right? Then regardless of what the closest k vectors are, this predicted distribution is not going to be relevant at all, right? Like what if this was just never seen before at all at training time? So if your data store doesn't have coverage, then this predicted distribution could be very messed up.
The vector representation in the third column, isn't that encoding both the prefix in the source language and the generated
Yeah.
target language?
Yeah.
It's encoding both of them.
Well, so remember this is at training time. So these are not generated tokens. They're just prefixes of the ground truth translation. But yeah, I mean, this is from the decoder, but the decoder does cross attention. So it has information about the source as well. Okay, yeah.
And the decoder was pre-trained on some other task, right?
No. So you assume that you just trained a machine translation system on this training data. So the encoder and decoder model have been trained on this exact training data of French to English. You, after training, just run all of your training data through this trained model and then cache the vectors that you get. And that forms your data store for this setup. Okay, any other questions? Okay, so what do we do, going back to your point, when we don't actually retrieve anything that is relevant to this vector? Then we can't just rely on this predicted distribution because it's not going to be relevant for a completely new test example. So we're going to call this the KNN distribution, or the K nearest neighbors distribution. This is what we obtain by retrieving over the training data. We essentially, to get around this problem, will interpolate this distribution with what our normal decoder would have predicted. So without any retrieval, I feed this into the softmax layer that I have trained using this training data, and that is going to give me a distribution that is separate from this retrieval-based one. So I actually have two distributions. One that comes from retrieving similar things in the training data, another that comes from what the decoder thinks is the right word given this specific test context. And you see that we use this lambda hyperparameter to interpolate between these two things. So in this paper, this is a fixed hyperparameter. I forget what exactly they set it to, but it makes quite a bit of difference. And you could also imagine learning this dynamically. So maybe for some inputs, you might want to rely heavily on the retrieval if it's been seen, if it looks like it's been seen a lot in the training data. But if not, if it's out of distribution, then perhaps you should rely heavily on the decoder's predicted distribution. So the cool thing about this whole setup is that it does not rely at all on training any new model. You can do this with any pre-trained language model or pre-trained machine translation model, as long as your model is producing token level vectors, which basically every model we've talked about in this class has been doing that. All right, so just to emphasize again, unlike the realm approach, this requires no training. And again, we're using one of these fast nearest neighbors or fast inner product libraries. This FACE library was released by Facebook, and it's very popular for these kinds of things. It supports both nearest neighbors, clustering, and other things like that. Okay, we have a question. Since we are retrieving from the training data, I wonder why PKNN and PMT would be much different. So if your machine translation model has learned to generalize to novel inputs, then you might expect that these two things could be much different. So even if this hasn't been seen before, like maybe an entity hasn't been seen before or something like that, you might expect that PMT will be able to produce the right subwords here that correspond to that entity, whereas PKNN is unable to produce those just because this hasn't been seen before. So that works not only with like tokens that are out of vocabulary for the training data, but also maybe syntactic structures and stuff that haven't been seen in the training data. It all depends on how much this MT model can generalize to held out data. All right, so as you can imagine, the one downside of this process is that it's very expensive because you are doing this retrieval at every token. So they say that during inference test time, retrieving 64 keys from a data store, which here is much bigger than the one you saw in Realm, because in Realm, you have one vector per passage. Here you have one vector per token in the decoder side. So their data store has billions of vectors in it. And you're retrieving from this data store after every token. So it results in a generation speed 2 orders of magnitude slower than not doing this. So in sum, it's not practically useful if you're interested in building an MT system right now, but you know, they have some nice analysis experiments that show promising directions in the future. First of all, despite the slow speed, it gives you improvements in BLEU score almost over most language pairs. So the improvements are not huge, but for some languages, they're you know, quite substantial, like Chinese to English, for example. It's over 3 BLEU points. And you can see the data store size here too. So for some of these, like English to German, we have a data store of 6.5 billion items, which is enormous. So you might be wondering, do I actually have to retrieve over every possible token in the data store, or can I downsample my data store to something smaller to make it faster while still getting the gains that I want? So they show you here, the blue curve is English to Chinese, and the red curve is Russian to English, and the y-axis is the difference in BLEU score when you increase the data store size. So here on the x-axis, it's what percentage of the data store is used during retrieval. So you can see, like, for English to Chinese, the curve is still going up as you add more and more things, but you can get a large chunk of this gain with a data store of just 20% of the size of the final one, which is 1.13 billion. And that's basically the same with Russian to English as well. So there's probably some point at which you can truncate your data store and still get most of the gains. Perhaps this could be made even more promising by intelligently selecting what goes into the data store rather than just randomly downsampling as they did here. All right, so finally, are there any last questions on the knn-MT system? Okay, I finally wanted to talk about a third task, long-form question answering, which involves generating answers to questions, which also has a retrieval component. So this project actually was one that my student Kalpesh worked on last year. So here, the task is you get this kind of open-ended question. The data set comes from the subreddit ELI5, or explain like I'm 5. So an example might be, why do humans need to eat many different kinds of foods to get their vitamins, but large animals like cows only need grass to survive? And on the Reddit, there are like many people who have been answering these questions. So some of these answers are highly upvoted, and those are kind of the ones that they choose in this data set. You can see that this is not a traditional span selection task. These questions are more complicated, and they also have an element of like simplification, because you want the answer to be understandable to a 5-year-old. That's the premise of the subreddit. Although you can argue that probably none of the answers here are actually understandable to 5-year-olds. I think in general it should just be understandable to a non-expert. So you can see the answer here. In addition to the efficiently breaking down grass thing and they eat a variety of plants thing, there's also the fact that blah, blah, blah. So this person clearly has some background knowledge about how human digestive systems work and how they differ from cows, and was able to write this answer. And so we would want a model that's able to do something similar. So this task of long form question answering, or LFQA, involves both retrieval as well as generation. So again, we can't expect that any language model has all of the knowledge necessary to answer any arbitrary question that is on the subreddit, especially since some of them are complicated and require expert knowledge. So to do this, we might imagine, retrieving a document like the Wikipedia article on ruminant, which I guess is the cow's stomach or something like that, and then also the human digestive system. And we might want to condition our language model on chunks from both of these retrieved documents so that it can leverage this external knowledge instead of have to do everything by itself. So this is challenging, right? Because the language model has to understand both of these articles and then also understand the salient differences between these two digestive systems. And then it has to summarize those differences in a paragraph. So this task is incredibly difficult. We don't really have any models that can solve this to any major degree. But basically, given the question and the retrieved documents, you want the language model to generate the answer. So a model for this task might be like a transformer language model, where you get the question, you concatenate it with one or more retrieved documents, and then you produce the ground truth answer during training. Just like in Realm, here you do not know the ground truth documents that you need to retrieve to answer a particular question. So you might need to also train a retriever. This is not like the knn-lm style where you don't have to do any training. Okay, so these kinds of tasks are evaluated by both retrieval quality as well as generation quality. So they evaluate retrieval by the team who collected this data set manually annotated several test set questions with the documents that you would need to retrieve from Wikipedia to have the relevant background knowledge necessary to answer this question. And then you can measure how well a trained retriever retrieved those particular documents. The generation quality, so how good was the answer, is measured through the Rouge score, which we saw earlier in the semester as a method to evaluate summarization systems, right? It's basically the recall variant of the blue score. So you can imagine that using something like the Rouge score, which is just looking at like word and n-gram overlap, is not a particularly good evaluation metric for a task like this. Why might you think that's the case? So why would I not want to use Rouge score to evaluate a model-generated answer with respect to this reference answer? I mean, there are long answers, but summaries, which Rouge is designed for, could also be fairly long. Any other idea? Yeah.
Because they're not trying to use similar words necessarily when they're in the original document, they want simpler words.
Yeah, so I think that's part of it, right? So the fact that they're trying to summarize and simplify all this information means that there's potentially huge variance in what is considered an acceptable answer, right? Like, you can imagine if you're using this answer as a reference, you would get penalized for not using the n-grams that are in this reference, but there are many different ways of phrasing this answer. There are probably additional facts that you could choose to put in here or take out here. You know, there's this example here. For example, humans make vitamin D because there aren't many food sources of it. That's a specific example that someone could choose to include in their answer, or use a different vitamin as an example, or use a completely different anecdote or something like that. So just the fact that this was written by a human does not mean that it consists of all the possible things that could comprise a reasonable answer to this question. So unlike summarization or translation, where the outputs are generally quite constrained, in this case, the outputs are not really constrained at all. And that makes it such that we don't right now have a reasonable evaluation method for this task. Rouge is just kind of something that's easy to compute, but probably not very meaningful on this data set. So I just wanted to highlight some of the problems with this task. So I'll skip over these results and just show you what needs to be done in order to make progress on this data set. So in our project, we were mainly focused on building a system that can generate plausible answers. But there are some issues with the data set construction process, which are kind of hard for the original creators to even know about, but which we found later by just like debugging our model outputs. Almost 80% of the questions in the training set have paraphrased versions in the test set. So it's very hard to check, right, if some question in training has also been asked in the test set, because they might not use the same words, but they are still asking the same thing. So here, the validation set has this question: can you protect electronics from EMPs or solar flares? If so, how? And then there's several questions in the training set about EMPs. Some of them have high overlap with this particular question. And so you can imagine a generation model that has been trained on these training questions could just spit out the answer to any of those and get some points here without having learned the actual underlying concept. So we also did some analysis on the Rouge score and how useful it is as an evaluation here. And we found that most of the time, if you just retrieve a random training set answer that is completely unrelated to the question, you can find many of these that get a higher Rouge score than the actual gold answer. So like this one is a random training set answer. It has some random n-gram overlap that allows it to get a higher Rouge score without actually being a good answer at all. And finally, like I think I want to highlight part D here. You could imagine, okay, we don't have any automatic metrics for this task. Let's have humans evaluate the output of generated systems. But it's actually very difficult to have humans evaluate these answers because it requires expert knowledge, right? You actually need to know how an EMP how you could protect something from an EMP in order to judge the correctness of an answer. So it's not like you can just go to Mechanical Turk and recruit some random person to rate this answer. You need someone who has expert knowledge or who is willing to learn the concept in order to judge the correctness. So I'll just end by saying that we have a really long way to go. This is one of the outputs from our system. The question was, why are almost all boats white? And it starts off pretty reasonable. Boats are generally painted white for obvious reasons. They're inexpensive and easy to clean. I mean, maybe that's not actually reasonable at all. Ships are also often painted to provide a visual contrast to the sea. So it starts off all right, although then it says many boats have an air breathing function that makes them easier to spot and stay afloat, which is a good thing if you're a pirate or trying to get into some country's waters. Not sure it's good if you're a pirate to be easy to spot. The Then it says, you can see some of these Reddit artifacts starting to creep in. There are many, many more reasons for why ships are white, but those are the ones that I know of. I'm sure there are many other reasons, but those are the ones I know of. So you have some repetition here, which we saw from our decoding algorithm lecture. Then you have this edit. I forgot to mention that the other answers about visibility and easy to see ports are also true. Ships are painted to appear to be larger and more expensive. That makes them appear more impressive, and so they are more likely to be bought by people who want to. That is a wild leap there. But yeah, I mean, this is definitely a very hard task. There have been improvements on this task since we made this paper, but there's still not a generally useful system that outputs correct answers that make sense. So future research direction. All right, so on Monday, we will do our midterm review. So I'll go over questions from the previous exams, and you should come prepared with any questions that you might have. We can go over them then. So see you then.